Now, continuing on with our tour of forces, we are going to focus on one that you are intimately familiar with, the friction force. So let's start with what we already know at this point. Remember that friction is a force that opposes sliding motion specifically between surfaces. So if we rub our hands back and forth, it's that force resisting as our hands slide, and it's always parallel to a surface. When my hands go back and forth, the surface is up and down, and I am sliding them in a parallel direction. Now, what exactly causes this friction force? Well, a lot of you are probably familiar with the details, but let's go ahead and say we have, for instance, here a box that's being pulled by a rope and it's sliding along the ground. And these might appear to be pretty smooth surfaces, but if we were to zoom in on the bottom of the box and the top of the ground here, we would actually see that there's a lot of little pits and crevices and cracks on these surfaces. They're really not that smooth at all. What is happening is that when these are moving past each other, essentially I've got these crevices and cracks, and they're getting hooked into each other. So ultimately, it's caused by the microscopic roughness of these surfaces getting caught on top of each other. Now, what's a couple ways we could try to alleviate this? Well, one, for instance, imagine that this is a slippery surface. We basically pour some water on it or something. Well, how does that reduce the friction? Well, that water is going to fill up these crevices and cracks and basically allow them to pass over each other much more easily. Similarly, you probably know, like at school, for instance, we wax the floors. And when you wax the floors, it can be really slippery because when we wax the floors, what we're really doing is we are grinding down these crevices and cracks, basically cutting off the edges of them and making them much more flat. So therefore they can pass over each other in a much less forceful manner. So let's talk about a very important question. Does friction always oppose motion? And you probably instinctually would say yes, because didn't I just say that a second ago with the definition of friction? Well, let's think about a scenario. Let's say that you are somewhere up in the north and you're walking along some ice and you're pulling this puppy dog on a sled. Well, a couple things here. First, let's consider you walking. Well, what allows you to walk forward? Well, if I think about it, you can go ahead and stand up if you want to. If to be able to push myself in the forward direction, I'm having to push against the ground backwards. Like take your foot and slide it backwards. You're sliding it back, getting it on the ground, and that's what allows you to push forward. So to be able to move forward, you're really having to push your feet back, and that propels your body forward. If there was no friction here and on ice, there's going to be very, very little. Your feet are just going to slide, and you're going to be basically like running in place. So we need that friction to even be able to walk. Similarly, consider this dog. Well, this dog is at rest on the sled as it's being pulled, but the dog is moving with the sled. And there must be friction between the dog and the sled in order to pull the dog forward. Because if there was not friction, well, what would happen? We would pull the sled, these two would not get caught on each other, and the dog would just basically fall right off as the sled would come out from under them. So there must be a friction force actually pulling the dog forward here. So when we have this question, does friction always oppose motion? Well, the answer is no. It specifically only opposes sliding motion. Now, word sliding is very, very crucial. We can still move, but how we move is basically we oppose that slide, allow things to get gripped onto each other, and that allows objects to be propelled back and forth. So what are the specific factors that affect the amount of friction in a given situation? Well, the first one is going to seem a little bit obvious. Ultimately, it comes down to how rough are the surfaces that are in contact with each other. Now, keep in mind that is surfaces, not surface. So, for instance, if I have like two pieces of ice, they're going to slide by each other probably pretty easily. If I have ice and rubber, maybe not slide quite as well. If I have rubber and rubber, they're not going to slide by each other well at all. So it's the two surfaces combined that matters here. And we measure this with something that's very crucial to know, which is called the coefficient of friction. Now, the coefficient of friction is abbreviated with a letter you probably haven't seen before. This is a Greek letter mu. That's spelled mu. It's pronounced mu, kind of like the Pokemon. And with this here, what we have, it basically looks like a U shape with a tail in front. I usually write it kind of like that. So that is mu. And if you have a higher coefficient of friction, that means we have more friction between the surfaces. Lower coefficient, we have less friction. Now, this is typically determined experimentally. There's not like some magical equation that tells us these two surfaces have this coefficient. Usually we have surfaces in the lab. Basically, people test them, moving them by each other, and we get tables of these mu values, these coefficient of friction values. But something very crucial I want to notice here is that this word, coefficient. Now, when you use coefficient in math class, it's typically just a number you stick in front of like a variable, for instance, like 2, 3, or whatever. And that's because coefficient really just means a number. It's not really a value. So that's going to help us remember that there are no units. It is actually a unitless value. It's one of the only times you can write a number in this class without a unit attached. Now there's something else that the surfaces depend on. So if I rub my hands back and forth, you're feeling some friction from the friction on your palms, for instance, the roughness. But how can you get even more friction between them? Well, you probably think, well, if I push my hands harder against each other, I get more of that friction. So if we grind the surface, we push really hard down, friction will increase. And in fact, that is true. How hard the surfaces are pushing on each other will also affect the amount of friction. And how can we measure this? Well, we do it with the normal force, that normal force being that perpendicular push force. If you all are familiar with this, for instance, with the example of a pencil. If you're trying to erase something, basically the rubber of the eraser and the paper, and if you just glide it over the paper lightly, you don't get much of an effect. To really get to erase, you have to really grind it down. It's not just the surfaces, but how hard you push too. Now there are two specific types of friction that we need to be familiar with. The first is known as kinetic friction. So what I have here is F little f comma K. So F little f means friction force. So this is really telling us the kinetic friction force with that little k. So the kinetic friction force in newtons is equal to this coefficient of kinetic friction. That's why it's mu little k. Remember that is unitless times the normal force in newtons. So what does kinetic mean? Well, you're all probably familiar with that term to an extent. That ultimately it means motion or movement. So kinetic friction is specifically the friction that emerges when two surfaces are moving past each other. Specifically when two surfaces are sliding past each other. Now the direction is always going to be opposite to the direction of the slide. So if I have these sliding past, this one's going this way, so its friction is going backwards. This one is going this way, its friction is going that direction. But the big thing here is you'll notice that, this is not going to change in a given scenario, and typically this is not going to change. So this kinetic friction value is always constant once we have found it. If we figure it out for one part of the scenario, it's going to remain constant throughout the scenario as long as the two surfaces are continuing to slide past each other. So let's go ahead and look at an example. Let's say we have this scenario as depicted right here. Then you are pulling a 20 kilogram tire at a constant velocity to the right across concrete. So the surfaces here would be rubber and concrete. If the kinetic coefficient of friction between these two is 0.6, what is the friction force on the tire? Well, how would we go about trying to do this? Well, first off, let's go ahead and write some net force equations in the x and y dimension after we construct an FBD. So this for a particular situation, the tire is going to be our object. It's going to be this dot. We've got gravity going down, a normal force from the surface pushing up. We are pulling it to the right, and the friction force therefore has to be to the left. It's in opposition to that sliding motion. And since we're pointing at a constant velocity, both of these force equations, some of the forces in the x and the y are both equal to 0. In the x direction, that's going to be the friction force plus the pull force is equal to 0. And in the y direction, the gravitational force plus the normal force is equal to 0. Well, how do we calculate the friction force? Well, we need the coefficient, which we have. We also need the normal force. And how can we figure out that one? Well, let's first look at the forces in the y dimension. Well, we know, just from what we just discussed previously, that the gravitational force is equal to the mass times the acceleration due to gravity, g. So we have the mass is 20 kilograms times the acceleration due to gravity, which is 10 meters per second squared. So the gravitational force is 200 newtons down. And because this has to be balanced with the normal force, that tells us that the normal force has to be 200 newtons up. Well, now that I have that, I can calculate the friction force. The kinetic friction force is going to be equal to the coefficient of kinetic friction times the normal force, or 0.6 times 200. Multiply those together, and we get a kinetic friction force of 120 newtons, specifically going to the left. Let's talk about something for a second. Let's say that, for instance, you're really into CrossFit or something, and you've got a really big tire that you're trying to slide along the ground. You're trying to push that. Well, initially, you go up and you push it. And unfortunately, you don't push it hard enough, and it simply does not move. Well, if the tire doesn't move, if we were going to draw an FBD for it, we would get something looking like this. We've got gravity in the normal force balanced in the y direction. And then in the x direction, we would say you've got your push force. Well, to keep things balanced, however hard you push, there must be a friction force in the opposite direction that is of the same magnitude. They have to be even, because if they weren't, the tire would start to accelerate. Now you'll notice I wrote F little s here, not K, because this is no longer kinetic. This is for a situation where the friction is involved with an object that is standing still. The surfaces are not moving past each other. And this is something that's going to be known as static friction specifically. Static meaning motionless. Okay, so we got that, and let's say you stop and you're like, you know what? I'm going to try this again, and you push even harder against the tire, but unfortunately, even though you push harder, this tire friction force is still too big, it does not have anything happen. Well, if we were to redraw the FBD, well, FG and the normal force, those didn't change. But you're now pushing harder, and the only way this can remain motionless and be balanced means that the static friction force had to get bigger. So we're already noticing that the static friction force, unlike the kinetic friction force, apparently can change value. In fact, let's say you get really tired and sweaty and you stop. So you're no longer pushing it. Well, what are the forces on the tire? Well, you've got the gravitational force and the normal force in the y direction, but you're not pushing it. And if you're not pushing it, there's no force to the right. And if there's no force to the right, there can't be a force to the left, or else the tire would start accelerating to the left. So if you're not pushing it, well, it appears that there's no friction force at all. So this brings us to our other type of friction, specifically static friction, which we're going to abbreviate F with a little f, comma s, for static friction force in newtons. Now this looks a little complicated, so let's go through the details step by step, this whole equation here. And really the big thing though is, first off, static friction, unlike kinetic friction, is saying that there is no motion involved. This is the friction force that occurs when surfaces are trying to slide past each other, but they're at rest relative to each other. And the big thing here is that the static friction force is what is known as a reactive force, meaning that the value is not going to be constant. The value really depends on other forces acting on the object. So we just saw a second ago that if you didn't even push the tire, that basically there was no force of you pushing to the right or left, well then there couldn't be a friction force to the right or left. So first off, the static friction force could be as small as 0. That would be our minimum situation, which is ultimately, as long as we're on a flat surface and there's nothing pushing or pulling it across the surface, well then there will be no friction between the object and the surface. Now, ultimately, that's the minimum. The maximum value we could have here would be, well, these two values multiplied together, where we have mu s, the coefficient of static friction, keeping in mind that that is unitless, and Fn being the normal force in newtons. So the absolute maximum we could have, notice this says max here, so this is the maximum static friction force you could have, is those two numbers multiplied together. So it's got the same form as the kinetic friction equation, except we have mu s rather than mu k. So the static friction force can be as low as 0, and then it can keep increasing as you push harder and harder and harder until we reach some maximum value. There has to be a maximum, or else you would never have anything sliding at all. So once again, let's return to our situation, and let's say you've started to push it again, and we kind of already saw this situation. Now you're pushing it to the right, and in the process you're causing the friction force, the static friction force, to go to the left. Those have to be equal because this tire is not moving. It's not accelerating in a horizontal direction. But let's say you push even harder until you get to the point where this is on the brink of moving. The tire is about to start sliding across the ground. We could even say, oh man, the tire is practically vibrating. It's so close to sliding. Well, this would be the point where we've reached the maximum static friction force. This would be the coefficient of static friction times the normal force. That would be this. And you must be pushing that hard. Well, let's say you push just a little bit harder. Well, if you push just a little bit harder, the system is going to start to move. You're going to start to push the tire. But if we're starting to push the tire, it's going to start sliding. And if it's starting to slide, well, that's no longer the static friction situation. I am now going to be in a kinetic friction situation. So as soon as I get to the point where right past I get it to start moving, well, all of a sudden these forces in the horizontal direction are going to change. Because basically this is now going to be a kinetic friction force rather than a static friction force, which means we're going to use the coefficient of kinetic friction rather than the coefficient of static friction for these particular surfaces. And what I want you to notice is that if we want to keep this moving at constant velocity, well, this kinetic friction force is oftentimes smaller than the maximum static friction force, so we don't have to push it nearly as hard. In other words, it takes a lot more force to basically break them apart and cause them to start sliding. Once they start sliding, you don't have to push as hard to keep it moving at a constant velocity. Now, I just kind of touched on this, but just to kind of show you an example, typically speaking, when we have two surfaces, the coefficient of static friction is going to be greater than the coefficient of kinetic friction. Can they be equal? Yes, so it's not enough to assume that a static one will always be bigger. But it's a kind of a good trend to think about. So for instance, looking here, if I have rubber on dry concrete, so that'd be like if you're driving your car, for instance, on a nice sunny day, the static friction coefficient is 1.0, but the kinetic, when the rubber is sliding against the concrete, is about 0.7. If it's wet, these go down. The static friction becomes 0.7, the kinetic becomes 0.5. So let's look at one final example before we're done. Let's say we had the same scenario that we had previously. We're pulling on a 20-kilogram tire, but this time it's at rest relative to the concrete. It's not sliding along the surface. And let's say that the static coefficient of friction between the rubber and the concrete is 0.8. Rather than, I think in the previous situation, it was 0.6 for the kinetic coefficient. And we want to know what's the friction force if you pull with 0 newtons of force, 100 newtons of force, or 200 newtons of force. So go ahead and pause. I want you to try this on your own. Then come back. Let's see how you did. Alright, well, hopefully you gave it a shot. And the first thing we really need to do here is we need to draw an FBD, we need to set up our net force equations, and really when it comes to this sort of thing, when you're trying to figure out is it sliding or not, the best thing we should do is solve for the maximum static friction force. So I'm going to go ahead and set up my FBD. It looks pretty much identical to what I did previously. We have the friction force and the pull force balanced in the x direction, the horizontal direction, gravitational force and normal force balanced in the y direction. And if we go ahead and look at this, well, the maximum static friction force, the maximum that static friction can be, we're keeping them at rest, would be the coefficient of static friction, 0.8, times the normal force, which we previously calculated was 200 newtons, which makes sense because Fg would be 20 times 10, or 200. The normal force balances that. So we multiply these two together, and we get a static friction force of 160 newtons to the left. That would be its maximum value. So the static friction force can go anywhere from 0 to 160. So if I pull on the tire with 0 newtons of force, basically not pulling it at all, well, what's the friction force? Well, if I don't pull, the tire is not going to move, so I better, if I don't have any forces to the right, there better not be any forces to the left, so the friction force is actually just going to be 0 here. The only forces acting on the tire would be the normal force and the gravitational force. But now, let's say you start pulling on it, and so you start pulling with 1 newton, it pulls 1 newton back, 2 newtons back. So if I pull with 100 newtons, the static friction force is going to be 100 newtons to the left. Alright, well let's now say that I pull on it with 160 newtons. Now it is about to break free. And then we pull out with more than that, specifically we pull out with 200 newtons of force. Well, if I pull out 200 newtons of force, that is greater than the static friction force. So we are going to break out of the static friction situation. The tire is going to start sliding. We don't care about static friction anymore, and so we are going to deal with the kinetic friction, which I believe we previously calculated as 120 newtons. So the kinetic friction would be really 120 newtons in this particular situation. So what are the main takeaways for this lesson on the friction force? Well, one, can we evaluate if friction is even present in a given scenario and evaluate what type of friction it is? Is it kinetic and they're sliding past each other? Is it static friction and they're trying to slide past each other but they're at rest relative to each other? Or is there no friction at all? Additionally, can we calculate the kinetic or static friction on an object based on the specifics of a physical scenario, using the coefficients of static and kinetic friction as well as the normal force, and keeping in mind that for the static friction force, that value can go from 0 to its maximum.